Hi students, now let us discuss about the nucleophilic substitution reactions of the alkyl halides. Alkyl halides with the general formula of Rx, halogen being a more electronegative atom gets a delta negative charge and the carbon gets a delta positive charge. So therefore, the bond is polar in alkyl halides, and any electron rich molecule, a nucleophile, can attack on the carbon because carbon is positively charged. It is electron deficient center. The most common reaction of the alkyl halides is the SN reaction, nucleophilic substitution reaction, in which a halogen can be lost by a nucleophile. Nucleophile can replace a halogen from the alkyl halide, and hence this is called as a nucleophilic substitution reaction. Nucleophile replacing the halogen from here as X negative, and you get the product here. This is called SN reaction because a nucleophile replaces the another nucleophile X negative from the alkyl halides. There are two types of nucleophilic substitution reactions on the basis of a mechanism, right? We have two types of SN reactions, SN2 and SN1. SN2 and SN1. It's also called as a bimolecular nucleophilic substitution reaction, and this is a unimolecular nucleophilic substitution reaction. Let us discuss about the mechanism, right? SN2 mechanism and the SN1 mechanism in detail. As in an SN2 mechanism, in a bimolecular nucleophilic substitution reaction, the nucleophile actually attacks at the carbon from the back side of the leaving group. Here the bromine is the leaving group, okay, this is the leaving group, and the hydroxide will approach the carbon because carbon is delta positively charged, bromine delta negative, okay. So this is the carbon is electron deficient center, hydroxide, the nucleophile will attack here at the back side and it forms a transition state. A transition state is formed, and then finally the bromine is lost as X negative and the hydroxide forms the bond with the carbon. In the transition state, when the hydroxide group approaches the carbon, it starts forming the bond. You know, the bond formation starts between the carbon and the hydroxide. At the same time, the bond between the carbon and the bromine, the halogen, that starts breaking. In the transition state, bond formation starts between the carbon and the hydroxide, bond breaking starts between the bromine and carbon, and finally when the bromine is lost, hydroxide forms the bond. These hydrogen atoms, they flip to the other side. So there is inversion of the configuration as well in the SN2 mechanism. This is called inversion, right? Configuration, inversion in the configuration. When you see the the groups attached from this side, they move to the other side, correct? We'll discuss about the inversion of configuration later on. So that means in the SN2 mechanism, what we find the transition state has been formed when the nucleophile attacks the leaving, the carbon at the 180 degree angle to the leaving group. Okay, remember the requirement here for the nucleophile to attack is at the 180 degree angle, correct? It should attack at the back side, not from the front side. Front side attack is not possible. Next point is, when the transition state has been formed, the transition state quickly converts into the product. This is quite fast. However, the formation of a transition state is slow, and the rate determining step is the slowest step here. So that means the rate of a reaction actually now it depends on the formation of a transition state here, okay. And in the formation of a transition state, we find two substances here, nucleophile and the substrate, the alkyl halide. So therefore, the rate of a reaction, we can say it depends on the concentration of a nucleophile, and it also depends on the concentration of a substrate. Here, the substrate is the alkyl halide. So there are two concentration terms. That's why we call it a bimolecular nucleophilic substitution. That's why this is called SN2, because the rate of reaction depends on the two concentration terms, the nucleophile and the hydroxide. Okay, now let's have a closer look of this SN2 reaction again. As I said, the hydroxide group should attack the leaving group from a 180 degree angle at the back side. Only then the transition state can be formed. okay, only then the transition state can be formed. Here also the same thing, you can see the groups, the 3 hydrogen atoms here, the chlorine is here, this is a tetrahedral molecule with the hybridization of sp3 actually, this carbon, okay. The hydroxide ion attacks, the nucleophile attacks here at the back end, from the 180-degree angle to the carbon to the chlorine, and transition state is formed. In the transition state, in this TS, the transition state, what do you get actually? You get the carbon with the sp2 hybridization. It's actually highly unstable. Okay, the transition state is very highly unstable, we know it. But in this transition state, the hybridization of the carbon changes from sp3 to sp2, and that's why the groups here, the hydrogen atoms here, the groups attached to the carbon, they are actually now plane, in one plane. Now here they are not in the plane, right? But right now they are in the plane. And in the transition state, the chlorine is attached with the carbon, but not completely. Hydroxide again forms a bond, starts forming a bond, but this is not a complete bond here again. And then this quickly converts into the product with the loss of a chlorine as the Cl negative here, as Cl negative, and the hydroxide forms a bond, and what we find again, the hybridization is here sp3. However, from the starting material you can find the hydrogen atoms are from this side, now the hydrogen atoms are from this side. So there is inversion in the configuration. The configuration does change in the SN2 mechanism. This is called as a Walden inversion, right? Okay, fine. We'll discuss about it later on. Front side attack is not possible. The front side, why hydroxide can, should attack only from the back side? Because from the front side it's not possible. The chlorine with the Cl negative, the chlorine with delta negative charge, it will repel the hydroxide. So that means this attack from the front side attack is not possible, right? That's why we do not see the front side attack, okay, in the SN2 mechanism. So that's why this is not possible, okay. This type of a mechanism we do not see. Always it's from the back side, at the nucleophile should attack at the back end at 180-degree angle. Next point is the requirements for the SN2 reaction actually, or that the carbon, to which the hydroxide, the nucleophile will attack and form a transition state, okay, is going to form a transition state in which the carbon, is actually bonded. Now it starts forming a bond with the hydroxide. The requirement is that the group, the size of this group should be small. If you have a tertiary alkyl halide, the attack is not possible, right? So if you have, suppose, the 3 methyl groups attached here, the hydroxide ion will find it difficult to approach to the chlorine and form a transition state. In that case, the transition state will not be formed. That means if you have a tertiary alkyl halide, SN2 mechanism is not possible, because hydroxide finds it difficult to approach to the carbon because of the steric hindrances between the groups here and the nucleophile. They will repel it. If the size is small, right? If the size of these groups here is small, okay, if the size of these groups is small, then hydroxide will approach. And what we find the SN2 mechanism is possible only if you have a halogen and you have, suppose, 3 hydrogen atoms, means you have a methyl alkyl halide, or you have a 1-degree alkyl halide. In the 1 degree we have a 1 alkyl group, okay, or you have a secondary, it's also possible there, right? Also possible there with the secondary one, with the secondary alkyl halide. However, most easily the SN2 is favored with the methyl alkyl halide and the primary alkyl halide, correct? It can occur here, the nucleophile can approach here also, it can approach this carbon, also in this one also, but in the secondary one it's little bit some other requirements as well. However, most easily it's possible with the 0 degree, you can say 0 degree alkyl halide and the 1 degree alkyl halide. For the tertiary it does not occur, right? If you have a tertiary alkyl halide, it's very difficult for the nucleophile to approach, and therefore we say that a nucleophile cannot approach the carbon here due to the steric hindrance. So that means this SN2 mechanism is not possible for the tertiary alkyl halide, for the 3 degree alkyl halide. and we will later on discuss that the tertiary alkyl halides actually undergo SN1 mechanism, right? They follow the SN1. We will discuss about it later on in the next video what the SN1 is. But 0 degree, 1 degree, they follow the SN2 mechanism, right? Nucleophilic, bimolecular nucleophilic substitution reaction. While at the secondary alkyl halide, very interesting, we'll discuss about it as well. The secondary actually it can follow SN1 and SN2 both, depending on some other requirements, correct? Now, these are the requirements for the SN1 and SN2 in terms of structural requirements, correct? So 0 degree alkyl halide and the 1 degree alkyl halide, methyl alkyl halides and the primary alkyl halides can undergo the SN2 mechanism, right? Not the tertiary alkyl halides, right? They find it difficult. Okay, this is the energy requirement. This is the energy change. How does the energy change? Alkyl halides, when they form a transition state, this is highly unstable, okay? And then once the product is formed, you get a very low energy molecule. And again, here you can just see in this molecule the hybridization is what? Here the hybridization is sp3. In the product also the sp3, right? sp3, okay? But there is a difference in the structure, right? You can see the groups now from the other side. You see the groups from here, now the groups are from the other side, okay? With the nucleophile coming at the 180 degree angle to the leaving group and form the transition state, right? In the transition state, the hybridization is what? sp2, planar, right? So the groups here, this one, and this one, they are in plane, including the carbon. And that's why we find here, if this is the R configuration, this is the S configuration, there is an inversion of the configuration in the SN2 mechanism, right? This is the main characteristic feature, right? SN2 mechanism, there is inversion of configuration. The groups which are from this side, now they shift to the other side, okay? They shift to the other side. So there is complete inversion. There is complete inversion in the SN2 mechanism. Hope you got the concept. Thanks for watching the video. See you in the next lesson. Bye for now.